Hello, I am Harshita Ravindra. Today I'll be presenting my research work done under the guidance of Professor Jayashree Walson Nair titled Spatial and Visual Analytics for Grouped Analysis of Population Survey Data. In our doctoral work, we have explored novel ways of studying grouped variables for different scenarios, including their spatial analysis and visualization. Outline of the presentation today. In our doctoral work, we explored novel ways of studying grouped variables for different scenarios, including their statistical analysis and visualization. We propose grouping of data at the raw question level or the outcome variable level across two or more surveys. Here, we try to answer some of the research questions. Which spatial analysis and visualization design works best for large-scale population survey data, and how can we group and analyze large-scale population survey data in combination of visual analytics and spatial statistics. These are some of the population health surveys that needs to be studied extensively, and these are used as a case study in our work. We have used data from the large-scale National Population Health Survey in India, namely NFHS4 and CNNS. NFHS4, implemented during 2015-16, provides information on population, health, and nutrition for men, women, and children under 5 for all states and union territories in India. CNNS, implemented during 2016-18, is the largest exhaustive nutrition survey including micronutrients focused on all children under 18 years of age. Both surveys overlap in the coverage of nutrition indicators of children under 5. The summary analysis reports have been published for both surveys, and the raw anonymized household level data is available only for the NFHS form. Our work is used to study malnutrition of children under 5 in India and states of India. We use our methodologies to identify potential indicators and contextual factors for identifying high-risk regions of under 5 children malnutrition and help government and policymakers can use these for better decision making. In our work, we use group analysis to address multiple ways of integrating questionnaire. Here we use 3 ways to perform group analysis: survey integration, visual composition, and grouping questionnaire for improving visualizations. Spatial statistical analysis is extensively used in our work to analyze spatial distribution, patterns, and relationships in the population survey data, and the spatial autocorrelation being one of the extensively used in literature to analyze spatial data. Spatial autocorrelation relates the value of the variable of interest in a given location with the value of the same variable in the surrounding location. Survey integration. Large-scale surveys are implemented to gather information about specific issues in the population. However, conducting national population survey for low and middle income countries with high population density becomes challenging. Some of their surveys tend to overlap in the outcome with spatial, temporal, or both scopes. Mining data jointly from surveys with significant overlap gives new insight while preserving its autonomy. Our work shows that such an integrated analysis is beneficial along with preliminary analysis of existing national surveys to find new insights while maintaining their autonomy. Our case study focuses on under 5 children malnutrition in India as recorded in the NFHS 4 and CNNS. Using integrated data mining for both surveys, we find the potential health indicators and contextual factors for identifying high risk regions of under 5 child malnutrition. Let us now discuss the comparable and integratable components of the surveys. Our three-step workflow consists of feasibility check, choosing variables for integration, and integration using spatial correlation and clustering. In first step, we check if the state-wise sample distributions for both surveys are equivalent, which against the state-wise population distribution latest official census taken in 2011 in the states. We then check if there are commonalities in the survey outcome for both surveys, indicating that the surveys can be integrated. In step 2, we look for indicators and contextual factors across surveys that can be meaningfully integrated. For this, the indicators and the factors must have sufficient spatial heterogeneity. In step 3, we complete the integrated analysis using the spatial autocorrelation. We use global Moroni and the localized cluster map using bivariant LISA computed using the local Moroni. We look at the metadata and the overall descriptive statistics, which is the mean standard deviation with the corresponding respondents of selected indicators and contextual factors and available distribution data on severity with given labels from NFHS4 and CNNS for the children under 5. We observe that the statistical descriptors of stunting, underweight, and wasting are comparable. Let us now discuss step 1 here. Our first step is to establish the feasibility of integrating the selected surveys. Region-wise grouping of 30 states and distribution of sample population covered in the surveys are shown in figure A and B, respectively. The state-wise occurrence of stunting, underweight, and wasting given in percentages is shown in the figure C. Figure C shows considerable differences between both surveys. However, given the comparable statistic descriptors, we now look at the similarities we find within the aggregate values. In addition to their absolute count, both the surveys have published data of the discrete probability distribution of the severity of each malnutrition condition, namely stunting, underweight, wasting, and anemia. Except for anemia, we have data available in the gender and urbanization based sampled groups, in addition to the total population. Hence, we find distribution distances for each subpopulation using Hellinger distance to quantify the similarities between the indicators across two surveys. Here, we observe that the state-wise distribution distances between the surveys are low. As the HTs are lower than 0.184 overall, much lower than the upper bound 1.0. Overall, we conclude that the two surveys can be integrated given the closeness in the time period of surveys and distribution for stunting, underweight, and wasting. Moving to the step 2, where our goal is to identify indicators and contextual factors uniquely present in each survey for integrated analysis. We choose immunization record and micronutrient deficiency for indicators of children under 5 and maternal illiteracy and poor sanitization facilities for contextual factors. Given the spatial local heterogeneity in undernutrition in India, we study that the region-based trends in variables exclusive to each of the surveys. The data plot is also compact in its nature. Here, a region-wise data plot has representing a state in the regions. Since spatial heterogeneity, since spatial local heterogeneity is a criteria for the variables we choose, we find that immunization record has limited heterogeneity given the uniform coverage for all vaccination in states within a region and across regions. Our integrated analysis of survey is based on spatial statistics. The global Moroni statistics for spatial autocorrelation between common indicators in both surveys for stunting, underweight, fasting, and anemia are given along with the bivariant LISA cluster maps in figure shown. We see that there is a low spatial heterogeneity which is statistically significant for stunting, underweight, and fasting. Our, bi- our bivariant LISA cluster analysis shows high risk regions with when both an indicators and contextual factors has high values. Bivariant LISA between unimproved sanitization, micronutrient deficiency show high risk cluster in western regions for folate, Rajasthan for low serum ferritin, large part of northern central regions for vitamin B12, and Jammu and Kashmir for zinc deficiency. Visual composition. Here we explored the use of visual composition views, which includes juxtaposition and superimposition as design patterns. For multivariate visualization of population data on maps, in the proposed work, the following comparative layouts are used. Juxtaposed views using vector and matrix layout for visual comparison of geospatial visualization, superposition layout for the overlay of geospatial visualization, and explicit encoding for the difference in the distribution of variables considered. Of these, explicit encoding and juxtaposed view use global comparison, and overlays use local ones. In this work, we propose using 4 design patterns to visualize the coexistence of contextually related and comparable outcomes of population survey. Hellinger distance in the chloroplasts, hotspot using spatial autocorrelation in chloroplasts, contour maps and heat maps using kernel density estimation, and finally overlay and scale-aware heat maps using kernel density estimation. We apply the proposed method in a case study of malnutrition in children under 5 as captured by the population survey from India, namely the NFHS4. Univariant LISA for a single outcome variable at a time compared against other using juxtaposed view in a vector layout as shown in the figure to the left side of the slide. Bivariant LISA for 2 outcome variables at a time where the pairwise chloroplasts are arranged in a matrix layout like the S-Plom matrix layout as shown in the right hand side of the slide. Details of this work has been accepted in this conference and it will be presented on a later day. Grouping questionnaires for improving visualization. Group questionnaire responses are the ones where the questions are to be grouped section-wise. These questionnaire responses might not just be yes or no, but also include don't know, refused, unknown, or any other additional options. Including these responses to the visualizations, better analysis for the person who does survey data analysis. The grouped categorical questionnaire responses are presented in the form of vector of responses from an individual. Our work has enabled us to look large-scale population survey by identifying different hidden patterns better. In summary, we show a proof of concept of integrating existing large scale population surveys benefiting the stakeholders. The integrated findings may have been otherwise soiled within the survey but are significant when observed together. Unlike other non-visual data analysis method, comparative visualization using our proposed vector and matrix layout for juxtaposition show the influence of spatial locality. We have calculated probability distribution of distance in a novel way using Hellinger distance, which is represented in a 2D histogram in a geospatial space. Finally, our grouping questionnaire help in improving visualization for better understanding. We acknowledge the kind support by the IBM University grant and the Mathematical Research Impact Center support grant by the Science and Engineering Board. The slides also include the references we have used, main references we have used in our work. We thank you for your attention. We close the talk with the conclusion slide. We are happy to take questions. Thank you.